on our guest speaker tonight. So for those who don't know, John Portune, Whiskey 6 NBC. He's done a few talks for us before, so I'd like to say a big thank you for John for joining us this evening as well. John was first licensed in 1965 and he became an extra in the United States in 1972. And he has quite a few commercial licenses in radio as well, and a physics degree from Oregon State University. John is now retired, but he was a television broadcast engineer and instructor for many years as well. And he's written over, I think John mentioned now to me, 50 articles for various ham radio magazines around the world. He volunteers his time and his expertise to clubs, and that's why we hooked into John, and we've lucky enough to get him on tonight as well. He also enjoys steam railroading, pipe organs, and he's a sushi enthusiast, as I think most of us are. So I'd like to now hand over to John, and John is going to take us through a Yagi design, simple Yagi design, and the 3 rules about Yagis. John, welcome.
Well, thank you for having me again. I enjoy doing this. I think this phase of my ham radio career, which has taken me through quite a few different aspects of ham radio, is probably the most satisfying, teaching things. And I do a lot of writing, so forth. Okay, let's share the screen here and go to this one. Here we go. Get rid of this stuff. Come on, get out of the way there. All right, slideshow from the beginning. There we go. And one more little move here. And shut that down. All right, you should be looking at the opening slide of this presentation. Is that correct?
That is correct, John. Thank you.
Okay. Designing a homebrew Yagi is easy. Now that might seem sound like a misnomer or an oxymoron, but it is not. But it is absolutely true. I know a lot of hams, and me for many years, would never have thought about designing a Yagi. I might have looked up in a book on how to build one and followed a cookbook. But the idea of me just sitting down and designing one for myself never occurred to me, because I thought, well, only big high-powered engineers can do that. But I'm going to show you that's just not true. And in fact, I have published on this. This article was actually requested of me, and it ran in the American Radio Relay League's magazine up to now, and I do this as a presentation. It's a fairly popular presentation. And I'm going to give you a simple example here of how you can easily build a homebrew Yagi yourself out of stuff you've got lying around and you don't even need to resort to, excuse me, sort of lots of fancy formulas, or even the calculators you find on the air. And by the way, if you want a copy of the slides you're looking at here today that I will use in this presentation, you can download them. Just go to my website, w6nbc.com, and append /slides to it. And all of these PowerPoint slides that you're seeing here today will come right down to you as a PDF file. In fact, all of the slides I use in all of my presentations are up there if you want to look at some of the other ones. I don't hide these PowerPoints. They're available to the ham community as you like. Okay. Well, we all know about the Yagi Yuda antenna. In fact, here's Shintaro Yuda and Hitatsu Yagi showing one of their original antennas. Interestingly, though, it wasn't Yagi himself on the right who invented this antenna and who's holding the prototype there. It was actually Yuda who came up with the idea, but his name didn't really get on this antenna. Yagi's name got on it. The reason was Yagi was the one that publicized the antenna and published it. So we know it today as a Yagi antenna, but probably more technically, it should be called a UDA antenna. The parasitic, the re-radiating parasitic beam, a byword in the radio community, not just ham radio. Well, we all know about beams and Yagi beams. Here's a bunch of them. On the upper left, the famous crossed 440 or UHF or 70 centimeter Yagi beam made by Arrow, crossed with a 2-meter Yagi beam. Very popular for doing ham satellite work. And we see across the top there a UHF commercial beam. And of course, the kind of beams a lot of us have. I don't have one because I live in a deed restricted community of mobile homes. So I can't have a big beam like that, though I'd like to. That's a Yagi, of course. And on the bottom left, a VHF 2-meter beam. And of course, television antennas, broadcast television antennas, which are becoming less common today than they used to be, are pretty much based on Yagis. And there's another VHF beam on the lower right there. They dominate the radio world. Yagi beams are everywhere. Well, I want to show you, and I think a lot of you know basically how a Yagi beam works, but I think these couple of slides are just worth repeating, simply because they're so demonstrative of the principle of how this antenna works. And I know some of you won't need this information, but some of you might like it. And it just re-cements the principle of this antenna in one's mind. And it's the principle of the Yagi antenna, or maybe the Yagi UDA, as it's more properly called, works by the principle of parasitic re-radiation. And that's what we're going to see here demonstrated. It all begins with a dipole, a half-wave dipole, the green element you see there in the middle, as we all know. And that's, of course, where the energy enters this antenna at the feed point there in the middle of the green element, called the driven element. And that's driven because that's where the energy comes in there at the 2 feed point terminals in the middle of the driven element. And the wave that comes off of that antenna radiates outward to the side, basically, of the driven element. UDA discovered that if you take another dipole similar to the driven element and you put it nearby, it will pick up a good bit of that energy coming off of the driven element parasitically. That's why it's called a parasitic beam. There's no connection in that element that you bring near. It picks it up by radiation. It absorbs energy if you put it near to the driven element. But immediately, because it creates current in that parasitic element, it immediately re-radiates the energy. But if, as UDA discovered, you make the length of that parasitic element a little different than the driven element, you will change the timing of when it re-radiates the energy it picked up from the driven element. If you make it a little shorter, it will delay the re-radiation of the energy. And if you combine those two factors, the shortening or the lengthening of that parasitic element and the placement of that parasitic element in respect to the driven element, the re-radiated wave, seen here as blue, will be in the case in one direction exactly in phase with the primary wave coming off of the driven element, as you see there. And that's what we call the forward direction of the Yagi beam. And the two waves, the primary wave and the re-radiated wave from the parasitic element, will be in phase in the forward direction and will add to each other and strengthen the wave. So the two elements now will have gain in the forward direction, but in the other direction, they will be out of phase. And this is the reverse direction. And there will be destructive or reductive addition. And there will be less gain in the reverse direction. So this is the basic principle of the Yagi antenna. And I think most of you probably know this in principle. I just think this is a nice diagram. It's part of an animated diagram. I'm just going to show you in the next slide, which illustrates this very graphically. And it's such a nice diagram that I thought I'd include it in this presentation. You can, of course, also do the same thing with another element on the other side called the reflector. Now, in this case, you make it a little longer, and therefore it now will delay the re-radiation of the signal. It again will pick up parasitically some of the energy set off by the driven element, and it will delay the re-radiation of it. So the parasitic radiation will be now slightly delayed. But again, it will cause in the forward direction, the two again to be in phase, and in the reverse direction, the two to be out of phase. So again, we get augmentation of the driven elements signal. In the forward direction, more gain, and destructive in the reverse direction, and therefore not so much gain. So the Yagi produces more gain in one direction and less gain in the opposite direction. Basic Yagi principle. Parasitic re-radiation. That's the principle of the antenna. Okay, that I think you all know in principle. But now let's take a look at it animated. I think this animated diagram is very nice to look at. Oh, what happened to it? Did I get rid of it? Anyway, we'll see it here. Anyway, from 1926 until 1948, even professional radio engineers didn't know how to build Yagis because even though there was some publishing done by Yagi and Yuta, not much. And so in the years from the development of the Yagi until 1948, the Yagi was pretty much of a mystery to even the professional radio engineers, and they knew the principle, but they didn't have any simple guidelines on how to build them. So they built them kind of by trial and error, and so they went by trial and error. They got it done. Hams, though, and they still are today, are afraid of Yagis. They think that only high-powered engineers can possibly design Yagis like this guy here. I hope that's not the average ham, but it makes a good cartoon anyway. Hams don't, it doesn't occur to most hams that I could just take some old curtain rods or some welding rod and go out in my workshop and throw together a Yagi that it would work. They'd probably think I'd just make a mess of it if I tried to do it myself. I'd have to be a high-powered engineer to design a really good Yagi. That's just not true. That's just not true. Fortunately, in 1948, the National Bureau of Standards here in the United States, now called NIST, the National Institute of Science and Technology, published a nomograph called the 688 bulletin that the National Bureau of Standards published. You can still get this. In fact, the 3 pages of it you see here is the copy I have of it. You can just go on the internet and search for the NBS 688. And that's what it looks like right down there on the left, still available on the internet. And it's the definitive study that the National Bureau of Standards did in 1948 when after the Second World War, they realized the Yagi was an important antenna. So they finally decided to study it carefully. And they did this major study in Sterling, Virginia, and in Boulder, Colorado, where the WWV Standards broadcast station is. They did careful study of it, and they published this definitive study. You can get a copy if you want it. You don't need it. You really don't need it. There's just, unless you want it, but it's got all the curves and the mathematics in it of how a Yagi works. There's a picture of one of their test Yagis up on a test stand. Okay, but if you want it, you can get a copy of it. I have a copy of it, and these 3 pages are from my copy of it. The only chart that I found in there that was of any value is the one you see there on the lower right, and I'll refer back to that later. Therefore, today, because of that study, there are now online many calculators. Maybe some of you have used one of the calculators where you go out on the internet and you get one of the Yagi calculators, and it'll tell you how long to make the elements and where to put them. You may have used one of these. And because not many hams have enough mathematical background to actually figure out how to do it with equations and all that other stuff, or all those graphs in that 688 study. So the most hams, if they're going to build a Yagi from scratch, probably use one of the calculators. But unfortunately, there's a lot of disagreement in those calculators. If you use one and compare it to another, you're probably going to find that they're not very similar. And hams are quite confused about those calculators, and they don't know which ones of them to use. But I'm going to tell you here, you don't need any of them. You don't need that NIST study, and you don't need all these the calculators that are online. They're all pretty much a waste of time as far as I'm concerned. It's very much easier to design a Yagi than it is to go any of those routes. Hams really need more simplification, and that's exactly what I'm going to give you today here. The simple rules to design a Yagi that's so close to what the best engineer can do that you won't be able to tell the difference. You only need two rules, two simple rules that any ham can remember, and then pick up some old curtain rods or pick up some brass welding rod or some aluminum tubing that you've got lying around. Go out in your workshop and whip up a Yagi that's so close to it to what the best engineer can design that nobody will know the difference. And here are the two rules. All you got to do is learn them. And once you learn them, you'll never not be able to build a good Yagi. You build all the spacing between them. Even though you'll see Yagis built otherwise, don't pay any attention to that. You space all the elements the same. You don't make some of them closer and some of them farther apart. You may get a little tiny bit of benefit by spacing them differently, but don't do it. Hams don't need to do that. If you want to build an excellent Yagi, make all of the spacing between the director, the driven element, the reflectors, whatever, all of them 2/10 of a wavelength. How do you get 2/10 of a wavelength? Just divide 300 by the frequency, and that'll give you the wavelength in meters. Turn meters into inches by dividing it by 39.37 inches, and you've got the distance, 2/10 of wavelength. On 2 meters, it's about 16 inches. On 440, it's about 12 inches. 2/10 of wavelength. All of the elements are spaced the same. Don't bother with different spacings. It won't buy you that much. And I know you'll see Yagis that are tapered, where the elements get shorter and shorter as you go farther out. Don't bother with that. It's a waste of time. Make all your elements the same length. All of the directors are 5% shorter, and the reflector is 5% longer. And by the way, don't bother with more than one reflector. It doesn't buy you very much. One reflector is all you need. Don't put 2 or 3 reflectors on it. You're not going to get much benefit from it. More directors, of course, on a Yagi are worthwhile. You'll get more gain out of directors than you will out of reflector. One reflector and as many directors as you like, but make the reflector 5% longer and make the directors, all of them, same length, 5% shorter, and you'll have an excellent Yagi that you won't be able to tell the difference. You say that's too simple. No, it's not too simple. I've proven it so many times. You can prove it with EasyNet or any of the modeling programs. And in practice, you can put it right up against commercial beams and it worked just as well. In fact, many commercial manufacturers use these two principles and don't bother with the fancy equations. So you may ask the question, suppose you use these two simple rules. Suppose you use the complex math and the elaborate graphs. We'll let that ring. Don't let that bother. It's my wife's cell phone. It'll stop ringing here in a minute. So what happens if you do use the complex math? What happens if you do use the elaborate graphs? You'll only get a Yagi that's just a little bit shorter and 5% more gain. That's the most you'll get out of a Yagi if you go through all of the math and all of the elaborate calculators and stuff. 5% gain, 5% shorter. That's not worth the powder and shot to blow it up. That's not worth your time. I don't trouble myself in ham radio with 5% better or worse than an antenna. The guy at the other end of the QSA won't possibly know the difference. Just to prove it, let me show you a couple of curves here. Some of you may be into antenna modeling. This is EasyNet. By the way, it's free these days. You don't have to pay for EasyNet anymore. You can get the professional models of EasyNet from the EasyNet site. Many of you already know this, but if you don't know this, you can get the professional models of EasyNet completely free now at the at easynet.com. Roy Llewellyn retired and decided to to stop selling the professional models. What do you see here? These are two radiation plots. In other words, the gain and directivity of two antennas. The red one, the red curve. This is, by the way, this is an azimuth plot, looking down from the top, as if you were looking at how the antenna radiates from the top. The antenna would be along the horizontal line in this diagram, looking down at it from the top. The red curve is for the Yagi, built with these simple rules that I've already pointed out to you. The simple rules that you can easily remember. But now, what's the blue curve? And this is the one that blew me right out of the water when I produced this blue curve. I went online one day. I wondered how good would this little simple rule Yagi be compared to the fancy calculators that you can get online that tell you how to build Yagis with different spacings and taperings and all of that fancy stuff. So I went online and I got the 5 best calculators I could find that were online, and I extracted all their data from a same 3-element Yagi that were all the same 3-element Yagi, and then I composited them and put the data back together and did a plot of the 5 best online calculators for Yagis that I could find online, and then let EasyNet plot that Yagi, and that's the blue curve. I was amazed. The little simple rules produced a better Yagi than the composite of the 5 best online calculators. Why trouble yourself with those online calculators, which make you taper the elements, make you space them differently? Waste of time. So how do you use these simple rules, which will give you a Yagi that's 95% as good as the best professional Yagi you can buy? Here's how you build a Yagi from these rules. Very simple. Get yourself a boom and mount a driven element on it and tune it up. Get it tuned up with your spectrum analyzer if you've got one, or if you've got a VNA, or if you've got an antenna analyzer. Put a driven element on a boom and tune it up so it's on band and you got a good SWR. Then add a director, a reflector, and a director or several directors if you want. Go ahead and put them on. Make the reflector 5% longer, make the director or directors 5% shorter, and space all of these elements 0.2 of a wavelength apart. Do that using the rules. So use the simple rules and do that. The next thing you do is you have to match the feed point. And I'm going to show you how to do that. In other words, get the SWR right. And by the way, you do that first. Don't adjust the frequency first. Adjust the SWR first. Always do that with all antennas. I think most hams, if asked, which do you adjust first when an antenna, the SWR or the frequency? The answer is always adjust the SWR first, then the frequency. Why? Because the SWR won't move much when you adjust the frequency. But if you adjust the frequency first, the SWR will go all off the map when you adjust the other way around. For any antenna, always adjust the SWR first. Anyway, so after you've got this Yagi built, put some matching on it, and there's various methods of matching. Adjust the SWR first, get it low, in other words, then trim the elements equally until you get it on frequency. Then if you need, go back and do a little tweak of the SWR. That's the basic tune-up procedure for tuning up a Yagi. It really is that easy. I like this picture. My wife found it a couple of years ago. I use it in a lot of my presentations. No, the book didn't say Yagi design on the front of it, didn't say anything. I put that on with Photoshop. Okay, let's look at some common matching methods for matching simple homebrew Yagis. There are three that I recommend, and I'll show the one I like the best. But the three common methods to match a Yagi: a gamma match. It's a good matching method, an excellent matching method, but I don't recommend it because it's a difficult to build method. Now, commercial manufacturers use it all the time. And if you buy a Yagi or an antenna with a gamma match on, it's a great match because it's easy to adjust. The ones I recommend for homebrew Yagis are either the J match or the hairpin match. My best recommendation is the hairpin. It's the easiest. But these are the matching methods that I commonly like. Okay, let's build. Let me show you a really cheap example of building a homebrew Yagi. First of all, don't use a round boom. Why? It's difficult to mount elements on a round boom. You might think a piece of PVC pipe, plastic pipe, garden variety water pipe. That's a good boom. Well, yes, it'll make a technically good boom, but it's hard to get the elements mounted on it. This is not one of my antennas, just a picture I got off the internet. This guy had to use a lot of plastic tape to hold his elements on the PVC boom. Now he used them, but imagine the Yagi worked well. But mounting, I like square booms or rectangular booms, much easier to mount elements on. Anyway, but we'll get to that in a minute. Here's a matching network that I want to show you. This is the J match. This is a good way to match a Yagi and very popular for homebrew Yagis. Notice that it looks like a J-pole, doesn't it? It looks like the driven element looks like a J-pole. And the matching and the connection to the coax, you can see the coax coming up the boom there. It connects, the shield connects to the end of the J element, which ends there at the boom, at the left arrow there. And the center conductor connects to the center of the driven element in which there is no gap. There is no gap in this method. There's no gap in the driven element there, in the full half wavelength driven element there. Just goes right on through it. It's a J-pole like structure. That's why it's called a J match. So you solder the center conductor just to the center of the half wave element, no gap, and then you solder the shield to the end of the J element. Makes an excellent match and very commonly used. Here is a commercial beam using a gamma match. Now, the gamma match is a great match, easy to adjust if you can build one, but they're hard to match, But the rectangular boom is, in my estimation, the best design. Unfortunately, it's hard to find rectangular materials to build things with. For commercial manufacturers, that's not so difficult. So this is a commercial boom. And by the way, notice that this commercial manufacturer is using the simple rules. All those elements are equally spaced, aren't they? And notice the reflector is 5% longer, and both the directors are 5% shorter. It's not a tapered beam. That commercially built beam is built with those simple rules and gamma matched. That's it. That shows you that these simple rules work very, very well. Even commercial manufacturers know it. But uses a square boom because it's easy to mount things on. You can put a screw through it really easily. What do I like for homebrew Yagis? Wood. You might say, oh no, I don't want to put wood out in the weather. It'll rot away and easily. No, just put a couple of coats of varnish on it, urethane varnish, and it'll last out in the weather for a long, long time, probably longer than you'll own the antenna. And by the way, here's another J match, and you can see where the transmission line, which is under the boom, gets soldered onto the center of the driven element, and the shield gets soldered to the end of the J match. This is simple 1x2 finished lumber, which you can buy at any lumber yard. So it's a very simple boom. How do you mount the elements? You just drill a hole through it, push the element through with a little adhesive on it, and it'll stand there forever. Excellent way to build Yagis. So here's an example. Again, this is continuing with the simple Yagi. How about the elements? What do you build the elements out of? Now here's my choice for what you build the elements out of. Some of you might think the best thing to build the elements out of would be copper tubing, or maybe aluminum or aluminium tubing if you can buy that at your local ironmongers or hardware store. Used to be able to buy aluminium tubing at the local hardware or ironmongers, but you can't get it so much anywhere. But auto parts stores have it as fuel tubing for car engines. You can often buy aluminium tubing at the local auto parts store. You might think, but that'd make great antenna tubing. It works fine. Or you might think solid house wire, THHN 14 gauge or 12 gauge solid house wire would make a good Yagi for home brew. Well, both of these would work fine. They'll make a technically good Yagi. The trouble with them is they're not very durable. They bend fairly easily. I don't recommend them for that reason. In fact, here's an example I took off the internet. This is not my Yagi. I just got this picture off the internet. I'm sure it worked fine, but using house wiring for the elements to me just isn't good. Even though it probably worked fine. I like the boom. That's 1x2 lumber, so I like that part of it. And he's got no matching on this at all. Here's what I recommend you use for the elements. What in the heck are these? Well, it's not aluminium tubing. It's not wire. Those are fiberglass rods. What are they used for? They're snow markers. If you live in snow country, and I don't think too many of you live in snow country, but here in the United States, we've got a lot of snow country. These are fiberglass rods, and they're available on Amazon. They're available either in 1/4 inch or 5/16 inch diameter, which it would be 6 or 8 millimeter, I think, 9 millimeter diameter fiberglass rods. They have a little reflective marker on it. That's the white piece. And they're used for people who live in snow country. When it snows, you can take these markers and just shove them in the snow to mark where your driveway is. And a lot of people use them. They're inexpensive, and you can buy a bundle of 10 for a very reasonable price. My wife saw me ordering driveway snow markers. We live on the coast of California where it hasn't snowed in the last 50 years. And she says, "Why are you ordering driveway snow markers?" She says, "Oh, I know. You're making an antenna." How do you turn those into antenna elements? Very simply. Here's, by the way, bicycle marker flags that you can buy in a lot of bicycle shops are also nice 1/4 inch fiberglass rods. How do you make those into antenna elements? you cover them up with aluminum foil tape, which is called high vac tape, heating and air conditioning vent tape, which you can buy down at the local hardware store. It's self-adhesive tape for taping up heating and air conditioning duct work. How does that work? Well, we all know that RF does not flow uniformly through a conductor. The magnetic field inside the conductor causes all of the RF to go to the surface of the conductor. Skin effect, it's called. In a conductor carrying RF, all of the current's flowing on the surface. The inside doesn't even have to be there. It can be a pure vacuum, or it certainly can be plastic. It can be PVC pipe. It can be fiberglass rod. And that's what I think that's why I use fiberglass rods covered with aluminum foil tape, self-adhesive tape, which you can get off the internet very easily. I buy 4-inch wide aluminum foil self-adhesive tape. It's called high vac tape off of the internet all the time. Amazon has it inexpensively. Buy it in 4 mil thickness, 3.5 or 4 mil thickness, which is to take care of the skin depth. And it's a little difficult to get it onto the rod, but here's how I do it. I take the tape, roll over the end and stick it and take off the covering on the back and just stick the ends of it down to a piece of carpet. Then I pull the rest of the covering off so that the adhesive surface is pointing up at me as in this picture. Then I take the driveway marker rod and push it down onto the glue surface and then roll it onto the tape. It's very easy to do once you practice it at first, because self-adhesive materials sometimes are a pain to get onto surfaces smoothly. Here are the dimensions of the 2 meter simple Yagi, showing you the hairpin and the mounting and the boom and the actual dimensions. As you'll notice, they're spaced 2/10 of wavelength apart, which on 2 meters is 16 inches. Again, that's 300 divided by the wavelength, converted, which will give it to you in meters, times 0.2 times 39.37 inches to turn meters into inches. And they're the actual dimensions in meters. Driven element is 37.5 inches, director 35.6, reflector 39.4. That's the length. And you'll notice it's 5% longer, 5% shorter. So, by the way, you don't need to write those dimensions down. Just go to w6nbc.com and /slides, and that slide will come down to you along with all the other slides as a PDF document. And you can see the little hairpin that I use for matching and the U-bolt that I use for mounting, and the pair of holes that allows you to mount it either horizontally or vertically, and a little ballon, which is right behind the driven element. We'll see more of that in a minute. The hairpin. What's the hairpin? The hairpin, you'll find out that most Yagis, without any matching on them, will end up to be a little bit low in resistance. The R will be something around about 35 ohms, and they'll be somewhat capacitive. So the actual impedance of most Yagis, if you just put a driven element and a reflector and a director on them, will end up being about 35 plus a few ohms minus a few ohms capacitive. You need to put a little bit of inductance across the feed point to cancel out that capacitive reactance. And that's very easily done with a hairpin. What's a hairpin? If you know anything about transmission line theory, you'll know that a shorted piece of transmission line acts like an inductor, acts like a coil. In theory, this little short piece of transmission line, which by the way is 2 inches wide, which fits right across that 2-inch piece, 1x2 piece of lumber to the 2 terminal screws that are drilled through the driven element, is 3 inches long, has just the right amount of inductance to match this little Yagi. how did I find out how long to make it? I just made several of them until I got rid of the inductance. I got a proper match. I didn't use any fancy formula. So don't send me an email asking me what's the formula for canceling that hairpin. I just got out some number 14 wire, pair of needle nose pliers, and I bent several of those horseshoes, those little horseshoe pins or hairpins, until I got a good match. It was that simple. It didn't take me 10 or 15 minutes to bend two or three of these until I got a good match. That's how I did it. I like pragmatic methods like that. I don't like I'm good at math. I've done a lot of math at university, but I prefer, like Albert Einstein, to do things pragmatically. How does the hairpin, how does the hairpin work? I've already mentioned it. In space, free space, a dipole is 72 ohms. But when you put a director and a reflector on it, the impedance changes at the feed point to about 35 ohms minus a little bit of capacitive. So it's the actual impedance of a typical 3-element Yagi is about 35 minus some number of ohms capacitive. So you need a little bit of inductance to readjust it, and it'll bring it right back to 50 ohms. So the hairpin is a little shorted piece of transmission line that does the job real slick. Bend a few of them, and you'll get right to a 1-to-1 SWR. Here's what it looks like. There's the boom. And there's the boom. There's two holes drilled through the driven element, which is the fiberglass rod with the aluminum foil on it. Those are 632 screws, or you could use 2BAs if that's the screws you've got. Anything that's about the right size. Drill holes through the boom, through the driven element, and they're 2 inches apart. That's sufficient to be on either side of the 1x2 lumber, and then there, and in the middle of the boom there, you can't see it, is a gap of about 1 inch. I just removed the foil in the middle. That's the gap. So you got the two quarter wave elements there, one above and one below. That's where the coax hooks up. The coax, and then the hairpin also connects right there. And again, that's the one, the 2x3 that I made. You can make those little hairpins so quickly that there's no need to try to calculate how long it is. Behind the driven element there is a little ballon, a little choke ballon, a little coax choke ballon. 4 turns and that's mini 8 coax. You can use RG58 if you want. I don't like 58. I prefer mini 8. It's considerably less loss than 58, but you can use 58 if you want. Two zip ties or zip tie wraps, one on top of the boom, one on the bottom of it, holds 4 turns on the boom quite easily. The boom has 4 holes bored through it, two vertically, 2 horizontally. This allows you to put a U-bolt big enough to go around whatever mast you use to mount this antenna on, to mount it either vertically or horizontally. The U-bolt here, this U-bolt here, I purchased from the bolt factory online. They sell stainless U-bolts in any size you want. But you can often buy them at marine supply stores and so forth. Even many ironmongers or hardware stores sell stainless U-bolts. And this allows you to mount the antenna horizontally or vertical. That's for a horizontal mount right there, if you want to mount the antenna horizontally. If you want to mount it vertically, then you put the U-bolt in the other 2 holes. And there's the finished antenna. It works really slick. As you see, you just run the coax down the piece of pipe. I mounted it on a piece of 2-inch PVC pipe. I used that as the mast. Held it up, holds up this little beam very easily. You can mount it on a metal mast if you want. I checked it on a metal mast, works fine on a metal mast. Or if you want, you can use a short PVC nipple, and then convert the PVC nipple to a metal mast a few inches down with a crossover clamp that you can buy at most hardware or most electronic parts stores. But it's a wonderful little beam. It works very, very well. A few coats of urethane varnish on the boom, and that beam will last as probably as long as you'll ever be using it. How about other bands? 220, 70 centimeters. The same principle works just as well. Let me show you the 70 centimeter one. Here's the 70 centimeter beam. The elements there are the driven elements about 12 inches long, little bit shorter, as of course they always are. The driven element is a little longer, and the reflector is a little longer. Driven elements is the director is a little 5% shorter, spaced 2/10 of wavelength apart. I had to move the balun and the U-bolt out from between the driven element and the reflector because they were interfering with the beam on 440. But at 2 meters, on 220, they can be inside. But on 440, it's best to put them behind the reflector. But worked fine. That's an excellent little antenna. If you want to use a short PVC nipple to mount the antenna on, although you can mount it, I tested it, you can mount it directly on a metal mast. You can use a double TV clamp and convert it down below the antenna about 18 inches. I want to test this idea. I want to test the same idea in circular polarization to use for ham satellite work. This is something I'm working on right now, a circularly polarized version of this same antenna for ham satellite work, where I mount a 2 meter one and a 440 one on the same here's on PVC. But I think that's quite possible. So I'm working on that right now. So here's the takeaway. Only 2 rules. And you're going to get a Yagi that's 95% as good as the most high-powered engineer in the world can build. Make all of your elements 2/10 of wavelength apart. Don't bother with different spacings. It isn't worth your time. Make all of the directors and the reflectors either 5% longer for reflectors, and directors, all of them 5% shorter, and you'll get a 95% as good Yagi. You no longer have to be afraid of Yagis. There now is a simple method. Not just high-powered engineers can build Yagis. You can do it with all sorts of old pieces of curtain rods or welding rods or anything you got, although I like fiberglass rods and aluminum foil tape. And that's it. You can get these slides again at w6nbc.com/slides. And that's my email address up top if you want to communicate with me. I'm at home most mornings, 7 a.m. to noon Pacific time at w6nbcmail@gmail.com. And that's my website, w6nbc.com. And that's it, folks. Have fun. Yagis are easy.